We're going to start talking about series. Now, series is a huge topic conversation, which is probably going to take me 8-9 videos to try to cover just a little bit of it. Now, a series is really just taking our sequences that we've seen in the past, but instead of just listing the terms in the sequence, we're going to add those terms up. Now, the notation that we use is we're going to use a capital sigma. Hopefully, you've seen this in the past. Let me get my eraser. Hopefully you've seen this in the past. And our capital sigma, it's really just a Greek capital S for sum. Now it has a bottom index and a top index. Let's just go to K for right now. So the bottom index tells you what letters the variable for this summation. So we have a variable of n. It tells you where it starts and where it ends. Now inside of here, just like our sequences, we have a generating function that tells you what to do. So this is telling us to do A1 plus A2 plus A3 all the way out to A sub K. Now this is a finite, a finite series because we're only adding up a finite terms. However, mostly what we're going to take a look at, we're going to take a look at infinite series. So we're going to add up an infinite number of things. This is going to go A1 plus A2 plus A3 all the way out forever. Now it may be a little bit counterintuitive to say, why would we even bother doing that? If you add up an infinite number of things, doesn't that have to equal to infinity? Well, no, it doesn't. In fact, quite often it adds up to a finite value. So what we need to do is take a look at this and decide what we mean by an infinite series, what it means to converge and diverge, because we're still going to use those words. Well, here's the idea. If the sum n equals something, doesn't have to be a 1, something to infinity of a sub n is equal to a value, and I'm going to call it s, then we say the sum n equals 1 to infinity a sub n converges else it diverges. Okay, so what does this mean? Really, all this means is if the sum actually ends up adding up to a finite value, then we say it converges, else we say it diverges. So just for our sake here, let's go ahead and put our negative infinity less than infinity. So you see what I mean, that it has to add up to a finite value. All right, now how do we actually go about showing this? Well, one way to do it is using something called the partial sums. Now this can be a little bit confusing because we're going to kind of mix our concept of what a sequence was with our new concept of what a series is. Partial sums mean this. Let's say that we are doing the sum n equals 1 to infinity of a sub n. Well, we're going to find some s sub n. Let's actually call it s sub k. Let's use another letter. S sub k as being the sum n equals 1 to k of a sub n. Now, what do we mean by this? Well, we're going to take our original infinite series, but we're not going to look at the entire summation all the way to infinity. We're only going to look at part of it. So s sub 1 would just be a sub 1, right? That would be because they would go from 1 to 1, so that'd be 1. S sub 2, so that means the top would go from 2, so we plug in 1, we plug in 2, so it'd be a sub 1 plus a sub 2. S sub 3 would be a1 plus a2 plus a3, so on and so forth. Now notice, these should all be finite values because we're adding up a finite number of terms on the right-hand side. So another way to define convergence, this is kind of the easy way, we can say this: if the sequence of s sub n converges, then the sum n equals 1 to infinity of a sub n converges. So here's the idea. I know it's a little weird because we're combining two different ideas. Here's the idea. If we just add up the first term, we get some value. We had the first 2 terms, we get a value. We had the first 3 terms, we get a value. Well, as we add up more and more terms, if that's approaching a value, so let's say the first one we added up was 1. The next one was 1 1/2, 1 3/4, 1 5/8, so on and so forth. We're getting a little bit bigger each time, but this has a limiting value, which means the sum is actually heading towards a value. So if that sum is heading towards a value, then we can say that that sum would converge. All right, the idea of whether or not a series converges or diverges is going to be the topic of conversation for quite a while. So let's take a look at a couple of ways that we can determine whether or not a series converges or diverges. Now, quick little side note right here. Pretty interesting thing that's going to happen throughout the next several lectures is we're actually going to be able to say, hey, does this sum n equals, I'm just going to make something up, of n squared plus 1. We're going to be able to say, does that converge or diverge? Basically, does it add up to a finite value or does it add up to an infinite value? We're actually going to be able to say whether or not it converges or diverges. But if we even say that it does add up to a finite value, rarely will we ever be able to say what that actual value is, which is kind of an interesting way of looking at it. We say, yeah, it adds up to a finite value, but I don't know what it is. All right, let's take a look at one specific type. This is called a telescoping series, and that's really what we're going to do throughout the rest of this chapter of these textbooks. Is we're going to take a look at a whole bunch of different series that have different names that kind of fit into categories. Here's the idea of a telescoping series. So let's say n equals 1 to infinity, 1 over n minus 1 over n plus 2. So there's our a sub n. Now, how do we tell whether or not this converges or diverges? Well, the idea for something like this is, let's start just writing out what this thing would be if we started to expand it. So what do we get if we plug 1 into this? This would be 1 over 1 minus 1 over 3 plus. So this was when, that doesn't work. Do I have another marker? Okay, so this is for our n equals 1. If n is equal to 2, what do we get when we plug it into this? This will be 1/2 minus 1/4. Okay, let's keep going for a little bit. If n is equal to 3, that's going to be, what, 1/3 minus 1/5 plus n equals 4. That's going to be 1/4 minus 1/6. Let's do maybe one more. If n is equal to 5, that's going to be 1/5 minus 1/7 plus. Now this is going to keep going forever. Well, notice something pretty interesting happens here. Hold on, I gotta grab a pen. Something pretty interesting happens here if we start taking a look at these terms. You notice here I have a 1, I have a negative 1/3, but over here I have a positive 1/3. So I know that that can reduce with that. Here I have a half. I don't have any halves over there, but I got a negative 1/4, positive 1/4. Negative 1/5, positive 1/5. And you can see negative 1/6, and you can see the negative one would be positive 1/6. The negative 1/7, positive 1/7. So you can see after this point, right here, we had a couple cancellations early, but everything after here is going to cancel eventually. So the idea is, well, this probably is going to add up to a finite value, right? Because we have some values here at the beginning, but everything else is going to cancel out. However, if you take a look at the last one, basically, which is just our formula, 1 over n minus 1 over n plus 2. You kind of think about this, this is where it gets a little bit abstract. As we go out to infinity, everything's going to cancel, and technically that one would cancel with 1 right over here. The last one you're going to have is that piece right there. Now, as long as n goes to infinity, that goes to 0, then this actually will add up. So if the limit as n goes to infinity, now I'm just going to generically say a sub n equals 0, then this would converge, right? This will add up to a finite value, right? If this goes away, all those things cancel, then this would just add up to be 1 plus 1/2, which would be 3/2. Now, that would be true as long as this actually goes to 0. And as we can see here, the limit as n goes to infinity, 1 over n plus 2 is 0, right? As n goes to infinity, n's getting bigger, the top stays the same thing here. So that goes to 0, which means this actually converges. And this is one of our few cases to where we can actually not only say that it converges, say that this thing actually adds up to be 3/2. So telescoping series are fairly interesting series, but they actually don't occur too often. They do show up, but not that often. So if you kind of see a difference like this, you're saying, well, that has a chance to be a telescoping series. So to figure out whether or not a telescoping series converges or diverges, write out a whole bunch of terms. It only takes a bunch. And then start canceling out and make sure that after some point, everything's going to cancel out. And if everything cancels out at a certain point, all you got to do is check that very last thing and make sure that that goes to 0. If that goes to 0, then the thing will converge, and it'll converge to whatever did not cancel out at the beginning. So telescoping series, pretty interesting type of series. But like I said, not very common. So let's take a look at a very common type of series that we also know quite a bit about. All right, let's see. Let's take a look at something called geometric series. Now, these are a type of series that show up quite a bit. A geometric series is any series that has this form. Sum n equals, I'm going to put a 0 here for now. I'll tell you why in a second. R, n. I know most of our series have started at 1, but technically they can start at anything. And just for stuff to work out a little bit nicer in our future, geometric series generally start at 0. That's kind of the idea for this. So this is called a geometric series, where you have some constant and some value raised to the nth power. So an example might be the sum n equals 0 to infinity 4 1/2 to the n. Notice we have some constant multiple and then some value raised to the nth power. This is called a geometric series. We can actually figure out not only whether or not, or under what conditions that this converges and diverges, but this is one of the few we can actually figure out what it actually adds up to. And I'm going to go ahead and do that for you real quick because it's a fairly neat little trick. If we take a look at the partial sums for these, so basically I'm going to take this formula, we're going to plug in 0, 1, 2, 3, 4, so on and so forth, all the way out till we get to some value. So if we plug in 0, that'll be a times r to the 0, which is 1, so that's just a. Then it'll be a r to the first, a r to the second, a r to the third, r is a little low, a r to the fourth, all the way out to the very last one in the partial sum would be a r, a sub a, there's no a sub a in there, sorry, a r to the n. Okay, so the idea here is we didn't go all the way out to infinity, we just went up to some value. I used the same letter n here, I probably shouldn't have, but we just went out to some value. Now if we wanted the whole thing, we'd have to let n go to infinity here. Now I'm going to take this same expression and I'm going to multiply both sides of that by r. Now when I multiply this side by r, I just get an r. If I multiply this side by an r, every one of the exponents goes up by 1. So this is a sub r, sorry, AR, plus AR squared, plus AR cubed, plus AR fourth, plus all the way out to AR to the n plus AR to the n plus 1. All right, let's see if this part makes sense, right? If I multiply by another power of r, that goes up by 1, which means the one before it would be, of course, 1 less. Now you're like, well, why would that be important? Well, now if I just do a little bit of arithmetic, let's do some subtraction. So on this side, if I do s sub n minus rs sub n, I'm just subtracting. What's going to happen when we reduce this side over here? Well, notice this would cancel with that, this would cancel with that, this would cancel with that, and go all the way down to this canceling with that. So what do we have left on the right-hand side? Well, on the first line, the only thing we have left is A minus, and the only thing we have left on the second line is AR to the n plus 1. All right, I'm going to do a couple steps of algebra because what did we want to know? We actually wanted to know what this added up to, so now I can actually solve and get a formula for S sub n. This is A minus A R to the n plus 1. Divide both sides by 1 minus R. So we get the sum is, I'm going to factor an A on the top, 1 minus R to the n plus 1 all over 1 minus R. Actually, you know what? I'm going to do it like this. This may look a little bit better. I'm going to write it like this. I'm going to write this as A over 1 minus R minus AR to the n plus 1 over 1 minus R. How do we do that? I'm going to do it one more way. I think you'll see it a little bit easier like this. What if I factor out A over 1 minus R? Let's see what I get. 1 minus R to the n plus 1. All right, I think this will be the easiest way. You could do it any of the three ways that I started to do it there. Well, let's factor that out, and you'll see you get the same result no matter what. Now, this is our partial sum. Now, notice the only thing that depends on the our index, our n, is this piece right here. Now, we want, if we want this to converge. Now remember, converge means add up to a finite value. What has to happen? So the idea is n goes to infinity. What has to happen with this expression? Well, again, there's no n's here, so really my question is, if the limit I'm looking at is limit as n goes to infinity of r to the n plus 1. What has to happen to that for it to equal a finite value? Well, if r is some number, watch. I say, let's let R be 7. That would be 7 to the n plus 1. As n goes to infinity, you can definitely see that's going to be 7 to the first, 7 to the second, 7 to the third, 7 to the fourth, 7 to the fifth. So that's getting giant really fast. So that's definitely going to go to infinity, so that won't work. What if it was just the number 1? Well, if that's the number 1, what do we get? We get 1 to the first, 1 to the second, 1 to the third, 1 to the fourth. That's just 1, 1, 1, 1, 1. Now remember what we're doing, we're adding these up, right? So what's 1 plus 1 plus 1 plus 1 plus 1? Well, that would be infinity. So that wouldn't work either, right? Because we don't want to add up an infinite number of things. However, if this was a fraction on the inside, let's say like 1/3, what would happen to that as n gets bigger? Well, that would be what, 1/3, 1/9, 1/27, 181, 1/243. So this is getting smaller and smaller and smaller. So as n goes to infinity, as long as, if we want this to converge, we need r to be a fraction. Does that make sense? It's got to be less than 1, right? So if r is less than 1, then it would go away, right? This would be 0. And we would just have this first piece left. Well, notice it wouldn't matter if it was positive or negative. So to make sure we don't care if it's positive or negative, we're just going to say the absolute value of it is less than 1. So if this is true, if the absolute value of r is less than 1, that means that is 0. And if that is 0, here, I'm going to write this, as n goes to infinity, then we can say this. The sum n equals 0 to infinity of AR to the n is equal to, well, if that's 0, all we have is 1 times that is A over 1 minus R. So in this case, we actually know what this geometric series actually adds up to. Now, of course, this is only true if the absolute value of R is less than 1. But that's a great result because we can actually just look at this right now and say, does this converge or diverge? Well, we got to recognize the form. You say, hey, that's a geometric series. R here is 1/2, so R is 1/2. That's less than 1, so this converges. And you're done. That's how quick and easy it can be. Now, in this case, we can actually find it out as well. So, determine if the following converges or diverges. If it converges, find the sum. All right, now I'm just going to grab the one we have right there since we've already talked about it. Let's go sum n equals 0 to infinity. What did I say there? 4 1/2 to the n. So again, all we have to do to say that this thing converges, it's going to be converges because we have r is equal to 1/2, which is less than 1. And what does this converge to? Well, we have our formula. It's up there. A, according to this, I'm going to point over here. A is the number in front of the thing to the power. R is the thing to the power. So this is A over 1 minus R. So this is 4 over 1/2, which is 8. So this sum actually adds up to 8. All right. Now, they can kind of disguise these a little bit when they're writing them out for you. They can do things like, let's do one more, same directions. Let's say I have the sum n equals 0 to infinity, 3 to the n over 4 to the n. All right, that just looks like two exponentials, a ratio of two exponentials, but we can actually rewrite this sum n equals 0 to infinity as 3/4 to the n. Now it looks like a geometric series. Our A is 1, our R here is 3/4, that's less than 1. So we can say that this converges, and not only that, we can say this converges to 1 minus 3/4, 1 over 1/4, which is 4. And you're done. So it can be very, very quick and easy to get that. Now there is one other thing that may show up with your geometric series. And what if we had something like this? N equals 1 to infinity. Let's do 2 1/3 to the n. Okay, so if we're given this geometric series, now the good news is we can still say whether or not it converges or diverges. This converges because our r is 1/3, which is less than 1. However, we cannot say that it's equal to, by the way, let me go ahead and put this up here. This is not equal to 2 over 1 minus 1/3. Well, you're saying, why not? Well, because this summation actually starts at 1. For this formula to work, it has to start at 0. So, a little bit of good news, we can actually make this happen. Here's kind of the idea, and we're going to use this backwards. If you have a summation, let's say 1 to infinity of, I'm going to just do n squared. At any point in the summation, if I just start plugging in, that'd be 1 squared plus 2 squared plus 3 squared. At any point in the summation, you can actually just stop and then write the rest as the summation. Right? Basically what I did is I wrote out the first 3 terms and left all the rest of them in a summation. Which means you can also do this backwards. Right? I can actually put this together with this and then start it at 3. So I could say this is also 1, 2 squared. I could put this back in there and call this the sum n equals 3 to infinity of n squared. So here's the idea. Let's show you how this works. For this to start at 0, here's what I want. I want the sum n equals 0 to infinity 2 1/3 to the n. This is what I want. But this starts at 1. So here's the idea. What would the first term be? What would the 0th term be if I plugged it in there? So let me get that out of there real quick. So here's what I have. N equals 1 to infinity 2 1/3. That is really messy. let's try again. Sum n equals 1 to infinity, 2 times 1/3 to the n. Well, I want this to start at 0. Well, what would we have if we had plugged 0 into here? Well, if I plug 0 in here, this would be 2 1/3 to the 0. Right, that would be what it would need for that. Of course, anything to 0 is 1, so that's really just 2. But I can't just add that in there, right? That's some value. I'd also have to subtract it as well, right? That's really nothing. So the -2 out here stays out front. Now I can combine this inside of here and say this is the sum n equals 0 to infinity, 2 times 1/3 to the n. Now the good news, if there is any, I now know what this summation is using our formula. This is now 2 over 1 minus 1/3. So this is -2 plus 2 over, what's that going to be? 1 minus, so it's 2/3. So this is -2 plus 3, which is 1. Okay, so if you're missing terms, and if this thing started at 2, you'd have to figure out what the first 2 are, put them in, and then subtract them away as well. But as long as it has the form for a geometric series, then generally you can find out what that sum is.